The morning of September 17, 1945, was unusually cool for the Kanto Plain. A thin autumn haze lay over Atsugi Airfield as a convoy of trucks moved slowly through the gates, their cargo covered beneath canvas sheets tied with hemp rope. The men riding beside those trucks were not soldiers. They carried notebooks, not rifles, slide rules, not swords, calipers, measuring tapes, technical manuals translated from English into hastily written kanji. These were engineers. Among them sat a man who had not slept in 2 days. Jiro Horikoshi was 43 years old, and he looked older. His face was drawn, the skin beneath his eyes darkened by exhaustion and something more difficult to name. He had spent the last week trying to prepare himself for what he was about to see. He had read the intelligence summaries. He had studied the capture performance data. He had reviewed, more times than he could count, the after-action reports filed by pilots who had encountered the aircraft now waiting for him behind those canvas sheets. None of it had prepared him. Horikoshi was a man who had designed the Mitsubishi A6M0. He had given the Imperial Japanese Navy the finest carrier-based fighter aircraft in the world in 1940. He had solved problems that American and British engineers had declared unsolvable. He had built an aircraft that could fly 1,800 miles, outmaneuver anything in the sky, and destroy enemy formations with precision of a surgical instrument. He had been celebrated, awarded, written about in newspapers as a national hero. Now he was sitting in a truck, approaching a runway where 12 Grumman F6F Hellcats sat in a neat line, their blue paint still bright, their engines cold, waiting to be taken apart by the man whose creation they had spent 2 years destroying. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Hellcat had ended the Pacific Air War, not in the dramatic, singular way that popular history sometimes prefers. One decisive battle, one heroic moment, one turning point that changed everything. It had ended it the way an industrial process ends something, methodically, systematically, with the relentless efficiency of a machine that does not tire and does not doubt. Between August of 1943 and August of 1945, F-6F Hellcats destroyed 5,223 enemy aircraft in aerial combat. They lost 270 to enemy fighters. The kill ratio was 19.3 to 1. 12,275 Hellcats were produced in 30 months. At peak output, a new Hellcat rolled off Grumman's assembly line in Bethpage, New York, every 60 minutes. 24 hours a day, 7 days a week. The Japanese had produced approximately 6,000 Zeros between 1943 and 1945. Jiro Horikoshi knew these numbers. He had been given them by officers who delivered them with the blank faces of men delivering a terminal diagnosis. He had written them in his notebook and stared at them for hours, trying to understand not what they said, that was obvious, but why. Why had an aircraft that violated every principle of fighter design he had ever been taught defeated so completely, an aircraft that represented the highest expression of those same principles? That question was why he was here. That question was why the Imperial Japanese Navy's Bureau of Aeronautics had organized this technical inspection team in the weeks following the surrender, not for the Americans, for themselves, because the Japanese engineering community, the men who had designed and built the machines that had carried their nation into war, needed to understand what had happened to them, needed, in the most fundamental professional sense, to know where they had gone wrong, to understand what Horikoshi and his team found when they began their examination of the Hellcat. It is necessary to first understand the world from which they came, the philosophy that had shaped not only how Japan built aircraft, but how Japan thought about war, about technology, about the relationship between man and machine. The Zero had been born from a requirement that most Western aeronautical engineers considered impossible. In 1937, the Imperial Japanese Navy issued Specification 12 Sure for a new carrier-based fighter. The document asked for an aircraft with a maximum speed of over 500 kilometers per hour at 4,000 meters, a climb rate that would take it to 3,000 meters in 3.5 minutes, a range of over 2,000 kilometers with drop tanks, and maneuverability that would allow it to outturn any fighter then in existence. The Navy wanted all of this in a single airframe, a carrier-based airframe, which meant strict limits on wingspan and weight for deck operations. Mitsubishi's chief competitor, Nakajima, reviewed the specification and withdrew from the competition. Their engineers concluded it was physically impossible to meet all the requirements simultaneously without making fatal compromises elsewhere. The specification asked for too much. Something would have to give. Horikoshi disagreed, but he agreed that something would have to give. The question was what to sacrifice, and his answer was the answer that defined an entire generation of Japanese military aviation. Sacrifice protection. Sacrifice survivability. Give everything to performance. The result was the A6M0, which first flew on April 1st, 1939. It used an aluminum alloy called extra super duralumin, developed specifically by Sumitomo Metal Industries, which was lighter and stronger than anything comparable in Western aircraft design. It had no pilot armor, no self-sealing fuel tanks. The radio was frequently removed to save weight. Every non-essential system was stripped. Every rivet, every bracket, every structural component was engineered to the minimum weight consistent with the minimum safety margin. The Zero weighed 5,500 pounds empty. This was not an accident. It was a philosophy expressed in metal. And for 2 years, from December of 1941 to the summer of 1943, that philosophy had dominated every sky in the Pacific. The Zero's wing loading of 22 pounds per square foot gave it a turning radius of 612 feet. No Allied fighter could follow it through a turn. Its Nakajima engine produced 1,130 horsepower and pushed the aircraft to a maximum speed of 331 miles per hour at 14,900 feet. Its range was extraordinary. A Zero could fly from Rabaul to Guadalcanal and back, over 400 miles of open ocean in each direction, and still have fuel for combat. It was, by any objective technical measure, a masterpiece. Horikoshi had been told this so often that he had come to believe it completely. The captured Zero, tested by American engineers at NAS North Island in the fall of 1942, had reportedly astonished its evaluators. Lieutenant Commander Frederick Trapnell, the Navy's chief test pilot, had flown it and filed a report describing capabilities that seemed, to American engineers reviewing his findings, almost impossible to reconcile with the aircraft's modest engine output. But there had been warnings. There had always been warnings, if one knew how to read them. In the spring of 1942, Japanese naval intelligence had received fragments of a report circulating within Grumman Aircraft Engineering Corporation in Bethpage, New York. The report described a new fighter under development, the XF6F1, contracted by the Navy in June of 1941. The specifications that reached Japanese analysts described an aircraft with a maximum weight of approximately 12,000 pounds fully loaded, a Pratt & Whitney R 2800 double Wasp radial engine producing 2,000 horsepower, 6 Browning M2 machine guns, self-sealing fuel tanks, 212 pounds of pilot armor, bulletproof windscreen. Captain Minoru Genda, who had planned the Pearl Harbor attack and was widely regarded as the most brilliant tactical mind in Imperial Japanese Navy's air arm, reviewed these specifications and dismissed them. He described the proposed aircraft, according to accounts recorded in the post-war interrogations of Japanese officers conducted by the United States Strategic Bombing Survey, as an example of the American tendency to substitute machinery weight for pilot skill. The aircraft would be too heavy to maneuver, too heavy to climb. A Zero with trained pilots would destroy it. Genda was not alone in this assessment. The technical division of the Navy's Bureau of Aeronautics reviewed the same specifications and reached similar conclusions. An aircraft of that weight, with those wing dimensions, would have a wing loading of approximately 36 pounds per square foot, 64% higher than the Zeros. The turning radius would be enormous, the climb rate sluggish. Against the Zero, it would be defenseless in any sustained turning engagement. What the Japanese engineers failed to account for, what Genda failed to account for, what the Bureau of Aeronautics failed to account for, was that the Americans were not designing an aircraft to fight the last war. They were designing an aircraft to fight the next one. The first production, F6F, 3 Hellcat flew in October of 1942. The first combat mission was flown on August 31st, 1943. From the deck of USS Yorktown against Marcus Island. Within 30 days of entering combat, The Hellcat's kill ratios were generating after-action reports that were being read with considerable alarm by Japanese naval aviation commanders. Within 6 months, the patterns were undeniable, but the engineers had not yet had their turn. The systematic examination of captured American aircraft had been an ongoing activity throughout the war. Japanese technical teams had studied the Grumman F4F Wildcat, the Douglas SBD Dauntless, the Curtiss P-40 Warhawk. They had found in each case confirming evidence for what their doctrine already told them, that American aircraft prioritized structural robustness and firepower at the expense of performance characteristics that the Japanese considered decisive. The Americans built aircraft like they built cars. Heavy, reliable, powerful in crude industrial way, but lacking refinement that elevated a machine from merely functional to truly excellent. The Hellcat, when the first reasonably intact example became available for technical examination in late 1943, should have been more of the same, should have been further evidence for the conclusion already reached. It was not the technical team that conducted the first detailed examination of a captured F6F. 3 in early 1944 operated under conditions that complicated their work considerably. Fuel was scarce. Many of the most experienced aeronautical engineers were occupied with emergency projects attempting to develop countermeasures or successive designs. The examination was conducted under pressure, against a backdrop of operational losses that were already generating urgent demands from fleet commanders for answers that the engineers did not yet have. What they found when they opened that first Hellcat was not what they expected to find. The examination began, as such examinations always did, with the airframe. The first thing that struck the lead structural engineer, a man named Shiro Oda, who had worked on the early variants of the Zero, was the quality of the aluminum. American aircraft had been known to use lower-grade aluminum alloys than the extra super derailleur employed in Japanese designs, a fact that Japanese engineers had pointed to as evidence of their technical superiority. The Hellcat used a different alloy, designated 24ST by American manufacturers, which was not identical to extra super derailleur, but was, upon testing of samples taken from structural members, of comparable quality. More striking was how it was used. Where Japanese engineers had employed their superior alloy to achieve minimum weight, the Americans had used theirs to achieve maximum structural integrity. The Hellcat's wing spar was designed to a load factor of 9G, meaning the structure was certified to withstand forces 9 times the aircraft's weight before failure. The Zero's wing spar was designed to a significantly lower load factor. Oda had the numbers in front of him. He checked them twice and then a third time. The Hellcat had been built to survive things that would destroy a Zero, not just gunfire, maneuvers. This was the first revelation. The American pilots who had reported being able to follow Japanese fighters through maneuvers that seemed beyond the Hellcat's design limits were not exaggerating and had not encountered some exceptional example of the type. They were flying aircraft that had been deliberately engineered with structural margins generous enough to permit aggressive maneuvering that the performance specifications alone would not have predicted. The second revelation came when the team examined the engine installation. The Pratt & Whitney R2800 Double Wasp was, by any objective measure, a remarkable piece of machinery. It displaced 2,800 cubic inches across 18 cylinders arranged in 2 radial rows. In the F6F3, it produced 2,000 horsepower at sea level and maintained substantial output to high altitude through a 2-stage, 2-speed supercharger. Japanese engineers had known these specifications. What they had not fully appreciated was what 2,000 horsepower meant in practical terms when installed in an airframe of the Hellcat's dimensions and weight. A Japanese engineer named Kenichi Matsumura, who had worked on power plant integration for several Navy aircraft, performed the calculations with the precision that defined his profession. The Hellcat's power-to-weight ratio, the single most important determinant of climb performance and acceleration, was higher than the Zero's. The Zero's Nakajima Sakai engine produced 1,130 horsepower for an aircraft weighing approximately 5,500 pounds empty, or roughly 7,500 pounds in combat trim. This gave a power-to-weight ratio of approximately 0.15 horsepower per pound. The Hellcat's R2800 produced 2,000 horsepower for an aircraft weighing approximately 9,000 pounds empty, or approximately 12,000 pounds in combat trim. This gave a power-to-weight ratio of approximately 0.16 horsepower per pound. Matsumura set down his pencil and looked at the numbers for a long time. The Hellcat was heavier, substantially heavier. Everything the Japanese had been told, everything they had assumed, everything that had informed their dismissal of the aircraft when the first specifications arrived, was technically accurate. The Hellcat was indeed heavier, but it was not slower, not in a climb, not in a dive, and not in the acceleration phase of a diving attack. Because the Americans had simply installed a larger engine, an engine almost twice as powerful as the Zeros, and the power advantage had overcome the weight penalty entirely. This should not have been surprising. The arithmetic was not complicated, but it had been invisible behind the assumption that a heavy aircraft was, by definition, a slow aircraft. The Zero had been built on the principle that reducing weight was the only path to performance. The Americans had found a different path, increasing power. If you find the story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The examination of the Hellcat's armament installation produced a third revelation, and in some respects the most troubling. The F6F carried 6 Browning M2.50 caliber machine guns, 3 in each wing. Each gun was fed by a belt of 400 rounds. The combined rate of fire for all 6 guns was approximately 4,500 rounds per minute. Each .50 caliber round weighed approximately 1.6 ounces, with a muzzle velocity of approximately 2,900 feet per second. The kinetic energy delivered by a single round was devastating to aircraft structures not specifically designed to absorb it. The Zero carried 2 Type 99 20mm cannons and 2 Type 97 7.7mm machine guns. The 20mm cannon was, in terms of individual round energy, substantially more powerful than the American .50 caliber. A single 20mm explosive round could, under the right circumstances, destroy an aircraft with one hit, but the 20mm cannons had a rate of fire of approximately 500 rounds per minute each. The combined fire rate of the Zero's entire armament package was approximately 1,300 rounds per minute, less than one-third of the Hellcat's output. Japanese engineers examining captured gun camera footage alongside technical data understood the implication immediately. A Zero pilot who achieved a firing position on a Hellcat had a brief window in which to deliver a lethal quantity of ordnance. An American pilot who achieved a firing position on a Zero was delivering, every second, a quantity of metal that the Zero's unarmored airframe simply could not absorb. The Zero's design philosophy, which had sacrificed protection for performance, meant that the aircraft was catastrophically vulnerable to concentrated machine gun fire from multiple weapons. The Hellcat, by contrast, was not. The pilot sat behind 212 pounds of hardened steel armor plate. The seat back was armored. The headrest was armored. The fuel tanks were self-sealing, a construction technique in which multiple layers of rubber and fabric surrounded the fuel cell, allowing small caliber punctures to seal themselves automatically within seconds of being made. The windscreen was bulletproof glass. Oda, who had begun the examination in the methodical spirit of a professional seeking to understand, found himself sitting on a wing root at the end of the third day with his notebook in his lap, and a question he had not anticipated forming itself with uncomfortable clarity. The Zero had been designed on the assumption that the pilot was expendable, not in any callous or deliberate sense, but structurally, that the aircraft performance was more important than the pilot's survival, because a pilot flying a superior aircraft would not be in situations where survival was at issue. The design assumed invincibility. The protection systems, armor, self-sealing tanks, structural redundancy, had been judged unnecessary because the Zero would never be hit. The Hellcat had been designed on the opposite assumption, that the pilot would be hit, that the aircraft would absorb damage, and that both needed to survive the experience. It was a design philosophy that treated combat not as a duel between masters, each seeking the perfect killing stroke, but as an industrial process in which attrition was inevitable and the goal was to lose less than the enemy. Oda had been an engineer for 15 years. He had worked on the Zero from the early design phase, had understood its compromises, had accepted the philosophy that informed them. Sitting on that wing root in the autumn of 1945, he wrote a single sentence in his notebook that his family would find decades later among his papers. We designed for the pilot we wanted our men to be. They designed for the war as it actually was. The formal report of the technical inspection team, submitted to the Bureau of Aeronautics in November of 1945, ran to over 200 pages. It covered the airframe, power plant, armament, avionics, hydraulic systems, oxygen equipment, radio installation, and manufacturing processes observed in the examined examples. It was a thorough, professional document, written in precise technical language of men who had spent their careers in aeronautical engineering and who brought to this particular task both professional rigor and, reading between the lines of even its most technical passages, something that can only be described as grief. The avionics section deserved particular attention because it illuminated a dimension of the Hellcat's superiority that the combat reports had suggested, but that the engineers had not fully appreciated until they held the actual hardware in their hands. The F6F carried the N/ARC, one VHF radio system, which operated on frequencies between 156 and 174 megahertz. It provided clear voice communication between aircraft and between aircraft and ship, with a range adequate for coordinated fleet defense operations. The radio weighed approximately 30 pounds in its installed configuration, including the antenna leads. Japanese engineers had long known that American aircraft routinely carried radios of this type. They had also long known that Japanese aircraft frequently flew without functioning radios, or with radios of significantly lesser capability, often because the weight penalty had been judged excessive, or because the radio equipment available was insufficiently reliable in combat conditions. Pilots operating without reliable voice communication were restricted to visual signals, pre-brief formation tactics, and individual initiative. The N/ARC. One was not in itself the most sophisticated radio the Americans had produced. What mattered was not the radio alone, but the system it enabled. The fighter direction system used aboard American carrier task forces in 1943 and 1944 integrated shipboard radar, specifically the CXAM and later the SK series, with trained fighter direction officers who could communicate in real time with airborne pilots, direct them to intercept positions calculated from radar plots, and coordinate the deployment of multiple fighter divisions across a three-dimensional battle space extending to 50 miles and 30,000 feet altitude. The Japanese engineers understood the principle. What the examination of captured equipment, combined with interrogation reports from American officers who volunteered this information after surrender, forced them to understand was a practical consequence. A Japanese formation flying toward an American carrier task force was detectable from the moment it formed up. Its course, altitude, speed, and composition were known before its pilots had any knowledge of what was waiting for them. The Hellcats were not scrambled in response to Japanese attacks. They were prepositioned for interception. The engagement geometry, altitude advantage, sun position, approach vector, was not the result of Japanese mistakes or American luck. It was calculated, planned, and executed by a system. A senior engineer named Taro Fukuda, who had overseen radar development for the Navy's technical department during the war, read the section of the interrogation reports dealing with fighter direction and then wrote, in the margin of his copy, a phrase that was later cited in the official post-war assessment of Japanese technical intelligence failures. "We were not losing fights. We were walking into traps." Horikoshi himself spent 3 days examining the Hellcat before he wrote anything. He walked around it, under it. He lay on his back beneath the wing and looked up at the gear wells. He sat in the cockpit for nearly an hour on the first day, not touching the controls, simply looking. The other engineers gave him space. They understood what this was. He had designed the Zero when he was 37 years old. He had spent the following 5 years watching it fight, and watching it die. He had received reports. He had seen photographs. He had read the kill tallies that grew more catastrophic with every passing quarter. He had been asked, repeatedly, to design a successor that could restore Japanese aerial supremacy, and he had tried. The A-7M Reppu, the intended replacement for Zero, had suffered repeated delays, engineering compromises, and engine availability problems that reflected the broader collapse of Japanese industrial capacity in the war's final years. It had never reached operational deployment. Now, he was sitting in the cockpit of the machine that had destroyed everything he had built. The notes Horikoshi made during those 3 days of examination were published in edited form in his post-war memoir and in subsequent technical histories. They are worth dwelling on at length, not because they contain surprising technical revelations. The engineers have been building toward these conclusions for days, but because they represent the most articulate expression of what the Hellcat's examination meant to the people who had to reckon with it most directly. The first thing Horikoshi recorded was the quality of the manufacturing. He had expected American industrial production to be crude, the output of a mass production system that prioritized quantity over quality. What he found was the opposite. The machine's surfaces were precise. The tolerances on critical components were tight. The finish on structural components was, in many respects, superior to what Japanese manufacturers had been able to achieve at comparable production rates. He wrote, "This is not the work of a nation that is manufacturing carelessly. This is the work of a nation that has solved a problem we believed unsolvable: how to produce precision engineering at industrial scale." The second observation concerned the cockpit ergonomics. Japanese fighter cockpits had been designed to accommodate the physical dimensions of Japanese pilots, typically smaller in stature than American pilots, and had been laid out according to the principle that a skilled pilot would develop through training the ability to operate all controls efficiently regardless of their arrangement. The Zero's cockpit was functional but cramped, its instrument layout reflecting priorities of designers who assumed that the aircraft's superiority would limit the duration of combat encounters. The Hellcat's cockpit was larger, its instruments arranged with clarity and logical grouping that Horikoshi, despite everything, found himself admiring. The throttle quadrant was positioned for natural left-hand operation. The primary flight instruments were clustered in the center of the panel, where the pilot's eye naturally fell. The gun sight was an optical computing type, the Mark 23, which required the pilot to set the wingspan of the target aircraft and would then calculate the appropriate lead angle for deflection shooting automatically. A Zero pilot estimating deflection lead was doing, in his head, under G-forces and the stress of combat, a calculation the Hellcat pilot's gun sight was performing mechanically. Horikoshi wrote, "They have systematically removed from their pilots every task that could be performed by a machine. We have given our pilots every task, including those that machines can do better, because we trusted in pilot skill. They have trusted in pilot time. The time freed from calculation is time available for situational awareness, for coordination, for survival." The third and most extended observation concerned what Horikoshi called the philosophy of the second chance. The Zero had no second chances built into its design. A pilot who was hit did not have armor to absorb the round. A fuel tank that was punctured did not seal itself. An engine that was damaged did not have a redundancy to continue functioning. The Zero's design assumed that its performance would prevent it from being hit. If the assumption was correct, the pilot survived. If the assumption was wrong, the pilot died. There was no intermediate state. The Hellcat was engineered around the intermediate state. It anticipated being hit. It anticipated fuel tank punctures, pilot injury, structural damage, combat stress on the airframe beyond design limits, and it provided for survival in each case. The armor, the self-sealing tanks, the structural margins, the engine reliability, the R-2800 being famously capable of continued operation with multiple cylinders destroyed. All of these features added weight. All of them were the weight that Japanese designers had removed in pursuit of performance. And all of them, Horikoshi concluded, had been the difference between an air force that replenished its pilots and an air force that consumed them. He put this conclusion in the starkest possible terms in his notes. The Hellcat is not a better fighter than the Zero. In a turning engagement between equally skilled pilots at the same altitude and speed, the Zero retains advantages in maneuverability that the Hellcat cannot fully match. But this comparison is meaningless. The war was not decided by individual turning engagements between equally skilled pilots. It was decided by the cumulative effect of thousands of engagements in which the Hellcat pilot, having been hit, survived, returned, and fought again, while the Zero pilot, having been hit, died. We designed for the decisive single engagement. They designed for the long campaign. We were right about the engagement. They were right about the war. The formal examination concluded in late November of 1945. The report was filed, cataloged, and in the immediate post-war period, largely classified. The occupation authorities were not interested in facilitating detailed Japanese analysis of American military technology, though in practice the examination had been conducted with American knowledge and tacit approval. The strategic bombing survey teams were conducting parallel assessments of Japanese aircraft and technology, and a degree of mutual professional courtesy existed between the technical communities on both sides. Horikoshi continued to think about the Hellcat for the rest of his life. He wrote about it extensively in his memoir, Eagles of Mitsubishi, the story of the Zero fighter, published in Japanese in 1970 and translated into English in 1980. The book is remembered primarily as the story of the Zero's design and development, but its final chapters, dealing with the war's outcome and the lessons Horikoshi drew from it, constitute one of the most honest technical postmortems ever written by an engineer whose work was defeated. The passage most frequently cited by historians reads, in translation, "I have spent many years trying to understand how we lost. The answer I arrived at is painful but clear. We were not defeated by better pilots. In the early years, our pilots were superior by almost any measure. We were not defeated by a better aircraft in the absolute sense. The Zero remained, to the end, an aircraft of genuine excellence in the specific performance parameters for which it was designed. We were defeated by a better philosophy of warfare. The Americans understood that in a modern industrial war, what matters is not how many times you can win a fair fight. What matters is how many pilots you can put in the sky tomorrow." He continued, "Every feature of the Hellcat that we dismiss as excess weight, the armor, the self-sealing tanks, the redundant systems, the structural over-engineering, was a mechanism for keeping American pilots alive long enough to fight again. We saw these features as weaknesses. They were the source of American strength. The Hellcat did not defeat the Zero. American industrial democracy defeated Japanese warrior culture. The Hellcat was simply the mechanism." Genda, who had dismissed the Hellcat as a failure of American design in 1943, gave his own assessment in post-war interviews that were stark in their self-criticism. He acknowledged that the error had not been a failure of intelligence. The specifications the Japanese had received were accurate, but a failure of imagination. Japanese engineers and tacticians could not fully conceive of a warfare philosophy in which individual aircraft performance was secondary to system performance, in which the goal was not to build the best fighter, but to build the best fighter organization. They had evaluated the Hellcat as a machine. They had not understood it as a doctrine. Petty Officer Saburo Sakai, who had laughed at the Hellcat's weight specifications in the mess hall at Rabaul in September of 1943, who had survived a bullet through his skull and 4 hours of blind flight over the Pacific, who had flown combat against 15 Hellcats with one eye and the accumulated skill of 200 engagements, and who had survived because one American pilot forgot to jettison a drop tank. Sakai did not attend the technical examination. He was by then a private citizen. Beginning the transition to the quiet life he would lead for the remaining 55 years of his time on Earth. But he had reached his own version of the same conclusion, arrived at not through slide rules and calipers, but through the visceral experience of being outflown by a machine that weighed twice what his did. He had written in his diary, on the night after his combat over Iwo Jima in June of 1944, the sentence that captured the moment when pilot knowledge became engineer knowledge. "We perfected the sword while they built the gun. Now we wonder why we are dying." What Horikoshi and Sakai had independently understood, from their opposite directions, one through mathematics of the drawing board, the other through the mathematics of the kill ratio, was the same truth. The Zero had been designed to win battles. The Hellcat had been designed to win the war. In the abstract, this distinction is philosophical. In the Pacific between 1943 and 1945, it was the difference between 12,000 pilots who came home and 18,000 who did not. The Hellcat was retired from frontline service in the late 1940s, replaced by jets that made propeller-driven fighters obsolete in the same way the Hellcat had made the Zero obsolete. Not through any single decisive engagement, but through the accumulation of advantages that no amount of individual skill could overcome. Some Hellcats survived in second-line service into the 1950s. A small number were preserved in museums. A very small number are still flyable today, maintained by collectors and aviation enthusiasts who understand what these aircraft represent. Jiro Horikoshi died in January of 1982 at the age of 78. He had spent the last decades of his life as an engineering professor, teaching aeronautics at the Nagoya Institute of Technology. His students knew him as a meticulous, demanding instructor who insisted that engineering was not merely a technical discipline, but a philosophical one. That every decision made at the drawing board encoded assumptions about the world, and that those assumptions would be tested, eventually, in conditions a designer could not fully anticipate. He told his students more than once the lesson he had learned from a Hellcat, that the greatest danger in engineering is not ignorance, but certainty, the conviction that you have already understood the problem correctly, that your solution is optimal, that the enemy will engage you on your terms rather than developing terms of their own. He had been certain about the Zero. He had been wrong about the war. Saburo Sakai died on September 22nd in the year 2000 at the age of 84. He had become, in his final decades, an advocate for peace and reconciliation between Japan and the United States. He had corresponded with American pilots who had tried to kill him and been unable to, and with pilots he had tried to kill and had not succeeded. He had prayed, by his own account, for the souls of every man he had shot down. He had prayed also, which he mentioned less often in public, but which those who knew him understood, for the souls of his own comrades, the boys he had trained and sent to die in aircraft they barely knew how to fly, against an enemy that saw them on radar before they left the ground. In his final public interview, he was asked whether he believed the Zero had been a great aircraft. He thought for a long moment before answering. The Zero was a great aircraft, he said. The Hellcat was a great weapon. The difference is the difference between a sword and a gun. The sword requires years of mastery. The gun requires a different kind of mastery. The mastery of the men who designed it, the men who built it, the men who organized the system around it. We had masters of the sword. They had masters of the system. In the end, the system won. The system always wins. He paused again. The interviewer waited. But the swords were beautiful, Sakai said. I want people to remember that. They were beautiful. They were. The Zero was beautiful. Horikoshi had made something genuinely extraordinary, had solved problems that the best aeronautical engineers in the world had declared unsolvable, had given his nation an instrument of war that dominated the Pacific for nearly 2 years, and that, even in defeat, retained a kind of terrible elegance that those who flew against it never forgot. But the Hellcat was right. Not beautiful in the same way, not the refined expression of a design philosophy carried to its logical extreme, but right in a deeper, more durable sense. Right the way a well-organized supply chain is right. Right the way a radio network is right. Right the way a training program that sends pilots to combat with 300 hours and adequate gunnery practice is right. The technical examination that Horikoshi and his team conducted in the autumn of 1945 did not change the outcome of the war. That had been decided, irrevocably, by the time Horikoshi sat in the Hellcat's cockpit for the first time. What it did was something more modest and, in the long run, more important. It gave the engineers who had built the war's most beautiful fighter the precise understanding of why it had lost. They had designed for the pilot. They wanted their men to be. The Americans had designed for the war as it actually was. The mathematics were not cruel. They did not hate the Zero or the men who flew it. They simply did not care about them. The Hellcat's kill ratio of 19-1 was not a judgment on Japanese courage or Japanese skill, or the genuine excellence of the machine Horikoshi had spent his life building. It was a calculation. It was what happened when a design philosophy built on the assumption of invincibility met a design philosophy built on the assumption of attrition. And the two fought out across 2 years and 5,000 miles of Pacific sky. The sword met the gun. The gun won. The engineers finally understood why. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.